Okay, so we left off with orthogonality and Gram-Schmidt. We got through the Gram-Schmidt process yesterday, and then now we are left off with one problem. And so let's go ahead and get to the end of our notes here. There we go. So we've got a plane, and we want to use this applications of our Gram-Schmidt process and sort of the general theory behind it of how we're really just subtracting off parallel components in order to find a perpendicular vector. And moreover, if we are given a plane and we're given a point outside the plane, we can think of the point as a vector. So let's rewrite the problem since we've got extra stuff here at the bottom. Of course, this was an example, probably going to be on the final tomorrow or similar to that. So we've got our W, I guess we should say subset of R3 determined by this equation. So whenever we say W is determined by this, really another way of saying that, we mean that W is going to be a set of all vectors in R3 such that star is satisfied. And as I was mentioning yesterday, we can define our subspaces by multiple equations, right? If I had two equations where both equations need to be satisfied, W would be a one-parameter subspace, meaning a one-dimensional subspace at most. But likewise, we could generalize this to higher dimensions. So we've got our A was find the point on W. And we'll call that point Z. So Z on W, such that Z is closest to P. And I guess we should rewrite our point. P was 103. And then B, we want to find the distance between P and W. So if we want to follow these orthogonal projection methods, our first step was to actually parameterize W. In other words, we want to find a basis for W so that when we take a linear combination, a two-parameter family, we'll have a nice parameterization of W. And so we found that W is going to be the span of 101, -1, and 0, 1, 2. So hopefully you're familiar with how to do that, how to find the basis elements. It comes down to some basic elementary row operations, really. We could, of course, take our equations, write our systems of equations as a matrix transformation, and then, of course, use row operations to either row reduce and then determine basis elements in that regard. Now, the problem with our basis is that it's not normal, not orthogonal, I guess I should say. And so the problem with not having orthogonal bases, as I was explaining yesterday, is it kind of ruins this projection process. Since we want to be able to take a vector, we want this P, even though it's a point, we can turn it into a vector representing the vector from the zero, from the origin to that, pointing to that point, to break that vector down now into components parallel within W and then perpendicular to W. When we do that with our projections, but our projections won't work if the bases for W aren't orthogonal. The basis elements aren't. And as I was saying yesterday, they kind of get in each other's way, because then there's components of our basis elements within there. I guess we should say, yeah, there's non-perpendicular components. So there's parallel components of the basis elements with respect to each other. And if those are non-zero, well, then when we do our projections of P within those components, they're gonna shuffle things around and kind of get in each other's way. So let's go ahead and first create an orthonormal basis. Actually, I should say an orthogonal basis. We don't actually need to create a normal basis. And so that's simple enough, especially with only two vectors. Well, we have 1, 0. Let's give them names. Let's call them V1 and V2. And so let's just take V2 and find the perpendicular component. And so all we have to do is take V2 and subtract off the projection onto V1 of V2. Only got to do it once. And so we're going to have 0, 1, 2 minus our projection now. So we've got our dot product. Maybe we should have done our work in pieces. So let's write it out in the direction of V1. And so let's do our components maybe over here. I don't think we'll need a whole lot of space. V1 dot V2. We take a dot product, 0, 0, minus 2 is our dot product. And norm of V1. And actually, let's just compute the square of the norm of V1. That'll give us easier. 1 squared plus negative 1 squared is going to give us 2. That's basically all we need. So what do we got? We've got 0, 1, 2 minus dot product is negative 2 over 2 in the direction of V1, 1, 0, minus 1. That's just going to change the sign. So that's going to be 1 plus. And so what are we going to get? 1, 1, and 1. Check. If I take this guy, dot product with V1, do we get 0? Of course we do. And then anything else we should check? We should check that it's in the span of those two vectors. Of course, it's going to be in the span. If I just take the sum of those two vectors, we got this guy. So this vector is in W. And so now we can rewrite W as the span of 1, 0, negative 1, and 1, 1, 1. And this is our orthogonal basis. And now, since we have an orthogonal basis, we can project our y, which is simply the vector of the position vector of P. So turn the point into a vector. 1, 0, 3 were the coordinates. And we project that onto W. So how do we find that? So our y parallel is going to be the projection onto V1. Actually, let's call them different names. Let's call them U. This will be now U1 and U2, since we have different basis elements. So we project y onto U1 in the direction of U1, plus the projection onto U2 of y in the direction of U2. We know that this is going to have to be on W, since we are taking a linear combination of our basis elements. And so we just need to figure out these scalar multiples. Actually, well, so the notation's getting a little hairy. Sometimes when we talk about the projection, we mean the scalar projection. I think the way we've been using this in the book, the projection itself is a vector, and it's already in the direction of U. So we actually don't need that. It's kind of redundant notation there that I drew. The projection of y onto U1 is already a component in the direction of U1. Likewise, the projection of U2. So what are those scalar projections? Let's go ahead and compute those. We're going to have U1 dot y over norm of U1 squared in the direction of U1 plus U2 dot y in the direction of U2 so our U1 dot y is going to give us 1 minus 3, so negative 2. Norm of U1 squared, we showed already was 2. U2 dot y is going to give us, again, 3. I guess not again 3, but 3. And then...
Shouldn't it be 4?
4, yeah. I'm multiplying things. 4, and then U2 norm squared is going to give 3. So fill that in. We will have minus 2 over 2 in the direction of U1 plus 4/3 in the direction of U2. So we will get minus 101 plus 4/3, 4/3, 4/3. And that's going to give us 1/3, 4/3, and 7/3. And so this is our z. Now in this case, the scalar is important. You can write it as 1/3 times 147, but you do need to keep track of that scalar. Even though if we ignored that scalar, it would still give us a point on W, but we want the specific point closest to P. So this was part A. Find the point closest to it. Part B says find the distance. Since we found the point closest to it, the distance from P to W is now going to be the distance from P to Z. Which is fairly easy to compute. How do we compute the distance? It's going to be the length of the hypotenuse. So it's going to be the norm of our point 103 minus our vector 1/3, 4/3, and 7/3. So in other words, it's the length of y minus z. So hopefully everyone's kind of catching that. Of course, if we have z as our parallel component of y, so if we take y and subtract off the parallel component, we can also call this our y perpendicular. So this is the component, the perpendicular component of our y vector, the perpendicular component to w. And so the length of that is going to give us the distance of y to w. So it's just a matter of computing the norm of a vector. We've got 2/3 minus 4/3, and we'll have 9 minus 7, so 2/3 here. We want to compute the norm of that. And so we're just going to get 2/3. Actually, you know what? Let's factor out the 3. Let's do 1/3 times the square root of 2 squared plus 4 squared plus 2 squared. So 1/3 square root of 4 plus 16 plus 4. Square root of 24 is, I think the biggest multiple is 4 we can pull out, yeah? So that'll give us 2/3 root 6. About as simplified as we can get it. Any questions on that? Any questions on the procedure? Does anyone know the shortcut? So I'm sure a lot of you guys have had Calc 3. There is some shortcut, at least for part B. How do you find the distance between a point and a plane? In R3, there's a shortcut, namely that if we have some plane, W, and some point outside of W, so here's our origin. This guy we know is a normal vector. And so if we can actually find the normal vector of W, actually if we simply project P onto the normal vector, let's call P a vector. If we project P onto there, it'll give us that component. And so there could have been a shortcut for this problem if you are familiar with Calc 3, namely that if we are given one equation, it means that our normal vector is 1 minus 2, 1. As a check for ourselves, let's project P onto that. Now, actually what we want, if we're computing the distance, we want now the norm of this guy. So we want the length of the normal vector. And we can reduce that formula down a little bit. Since we'll compute the norm of that vector and it will cancel out one of those in the bottom. So P dot n is going to give us 4. And then norm of n squared is going to give us, norm of n, square root of 1 plus 4 plus 1. So square root of 6. And so it looks like what we're computing is our distance from P to W is now 4 over root 6. Did we get the same answer? Are we correct? We do have a root 6 in the denominator, which is not good, since our format on the other answer we got did not have a square root in the denominator. And so, of course, we see we get the same thing. Now, this last trick only works in 3 dimensions. And so maybe if we have time today, we'll talk about why this is the normal vector, why the coefficients of our defining equation for a plane give us a specific normal vector that actually kind of comes generally from the dot product. Now the problem is that we cannot use that trick if there are more dimensions, if it's 4 dimensions or higher. So fair warning, question on the midterm, it's going to be a plane, 2-dimensional plane in 4 dimensions. So I want you guys to actually use the techniques we're developing. So you will actually have to find the span. You'll have to find 2 linearly independent vectors from our system of equations that define our plane, and then go through the process. Create an orthogonal basis, and then project your vector onto it. So that way you're finding both the point on the plane that is closest, as well as then the distance from the point on the plane, from the point to the plane. All right. Let's see. Orthogonal complements we need to talk about. And orthogonal bases. So the last question, this will be, again, part of the question involving this problem on the midterm, will be to find the orthogonal complement So given a subspace, we define the orthogonal complement written W perp. It's just going to be the set of all vectors in Rn such that all the vectors in this set are going to be perpendicular to every vector in W. So any vector in W, find a vector perpendicular to all of those, and it will be in W perp. And so note, this W perp is a subspace of Rn. And I'm going to write W plus W perp is going to give us Rn. This plus, think of it like just a product where we have W cross. Think of it just as a tuple where we're taking all scalar multiples, all linear combinations of vectors in W. And then as well, I can take all linear combinations of vectors in W perp. Then it'll span the entire space. In other words, if, let's say, B is a basis for W and B perpendicular is a basis for W perp. So I have a basis for one of my subspaces, a basis for my other subspace. And now keep in mind, all of these vectors are perpendicular to here. And we could even make, we could create an orthogonal basis for W such that all of the vectors are mutually orthogonal. We could create an orthogonal basis for W perp in which all of these guys are mutually orthogonal. And then if I combine those two, so B union B perp is a basis for all of Rn. Example. So from the previous problem, let's describe W perpendicular, and let's find an orthogonal basis for that set. Use this to create an orthogonal basis for R3. I know that W, we already found, was the span of (1, 0, -1) and 1, 1, 1. This was our U1 and our U2. And we also know that this was orthogonal. I claim that we already found the perpendicular space. So I guess also to note from this, essentially what this means in terms of dimension is that the dimension of W plus the dimension of W perp is always going to be the dimension of the full space that they sit in. It's just kind of like a rank and nullity theorem that you can arrive at, especially if we're defining our subspaces in terms of equations. You can really think of this subspace W as the kernel of a linear transformation, and then likewise the subspace of W perpendicular as the kernel as well. So since we already have two basis elements that are orthogonal, we should expect the dimension of W perpendicular to just be 1. And I claim that we already found a perpendicular vector. And we know that from the previous problem, P minus Z, or I think I used Y to represent the vector of P. And we know that that is orthogonal to W, meaning it's orthogonal to both of those vectors, which implies that this Y minus Z, and so what vector was that? That was, we got 2/3 minus 4/3 and 2/3. And so we know that that vector is in W perp. And since we found one vector in a one-dimensional vector space, that is the vector. And if we wanted to simplify it now, since W perpendicular is the span of this entire vector, we can scale it if we want to make it look nicer. In this case, since we don't actually care about the length of the vector in terms of the entire subspace it spans. So we could write it as, let's see, we could factor out 1 minus 2, 1. Factor out a 2/3 from everything. Let's call this V, and I'm going to give it 3. I like to keep the indices on our basis elements going consecutively, but I like to use different letters when we're talking about the bases for different subspaces. So if we combine these two bases now, like if this were our B, and this were our, let's call it B1, and this one B2, now we know that R3 is going to be the span of the union of those two sets. Where now, what have we created, since these ones, since U1 and U2 were an orthogonal set, and this third one was mutually orthogonal to those two, the entire set is an orthogonal basis for R3. And we nicely kind of have them arranged where I know that the first collection of vectors, the first two, is going to be our subspace of W. Then the perpendicular complement, the span of V3, is going to be our V or W perpendicular. Any questions on that? So let's do one with 4 dimensions, at least to work with this. This one was fairly straightforward since we already had 2 vectors, and we actually found the third by this by using this process of finding the distance or finding the orthogonal component of a vector not on the space. So if we have to do this again, if we have, say, a four-dimensional space, so let's let W be (1, 0, 1, 0) and 0, 1, 0, 2 be our bases. We want to find the orthogonal basis, or find a basis and orthogonal basis for W perpendicular and use these two to find an orthogonal basis for R4. So these vectors are taken from the book. The question is modified a little bit slightly. The book actually has us use this vector y of 1, 2, 3, 4 and it has us go through the process we just did of finding the parallel and perpendicular components. But we don't have to use this point. We can actually use anything. Let's go ahead and start off doing this one, and then we'll generalize it, because the next step we will have to kind of generalize and actually formalize the process. The key idea is that really this vector y is not on W. So pick any vector that's not on W. That doesn't necessarily mean that that vector is in the orthogonal complement. It means from that vector, though, we can find the orthogonal component, and then the orthogonal component will be on the orthogonal complement. So what do we want to do? Let's take y and find the orthogonal part. So it's just going to be y minus the projection onto, again, let's label our vectors. Let's call them v1 and v2. So we project on the v1, subtract that off, project on the v2, and subtract that off. And so what are we left with? Our y, 1, 2, 3, 4, minus v1 dot y, norm of v1 squared, minus v2 dot y, in the direction of v2. So v1 dot y, what are we going to get? 1 and 3, so 4, over v1 squared is going to give us 2, minus our v2 dot y is going to give us 2 plus 8 is going to give us 10, divided by the norm of v2 is going to give us 5, norm squared of v2 in the direction of v2. So computing that, 1, 2, 3, 4, minus, we'll have 2, 0, 2, 0, minus 0, 2, 0, 4, and what do we get? Minus 1, 0, 1, and 0. So let's call this guy our U1. That'll be our first basis element for W perp. And if we take a look, when we take a dot product U1 with V1, it's going to be 0. And of course, dot product U1 with V2 is going to be 0 as well. So that is one good element. And so now the question is, how do we find another? Another basis vector for W perp. The answer is pick any vector not in the span of U1, U2, sorry. So not in the span V1, V2, and actually, sorry, let's rename this. I want to call it U3, just so we keep the numbers in order. So, right, those two span W. This is the starting vector that's going to be part of the span of W perp. We just need one more. So pick something else that's not in the span of those three vectors, and then make it orthogonal to everyone. So any vector will work. Maybe you want to choose a vector where the numbers will work out fairly reasonably. So in some sense, when we're taking these projections, we know norm of V1 was 2, norm of V2 is 5. The norm of our U3 is 2. So we kind of almost want to cook up the integers so that their dot products with the corresponding vectors will divide nicely. You don't have to. Any vector will work. So let's take a look. Let's actually write out the vectors all in one spot. So 1, 0, 1, 0. We've got 0, 1, 0, 2. And 1, 0, 1, 0. Well, I guess there's a couple ways we could do this. Sorry, there was a minus sign right there. This one, there's some workarounds. There's some shortcuts. Namely, if I know, like we know these two vectors are perpendicular. because even though they share the same components that are non-zero, negative reciprocal of each other, we do the same thing here. Egregious shortcut. I know that this is going to be perpendicular to those two because the non-zero components are the opposite. I know that this one's going to be perpendicular to that one because it's got the negative reciprocal of the coordinates that are non-zero. So that's an egregious shortcut for this problem. If we didn't know that, though, let's go through the process. So what you would want to do is just pick some vector not in the span. So let's say we start with a new vector. The last vector was 1, 2, 3, 4. That was a pretty good vector. What if we choose 4, 3, 2, 1? I don't know if the dot products will work out, but again, it doesn't quite matter. All you got to do is pick a vector that is not in the span, and since most of the vectors should not be in the span, if you pick by random chance, you should be pretty good. So just double check, right? If we wanted to get, I guess we could put this in a row and try to row reduce. So certainly this vector is not going to be in the span of the first two, because if it were in the span of the first two, then the first and third components would be the same. So we know that this is not on W. At least if it's not on W, we could come up with the orthogonal component. And again, this is going to be a fluke. If we come up with the orthogonal component to this from W, it will then be in W perpendicular. However, there is an off chance where it might be a scalar multiple of the one we already found. So you kind of just have to eyeball it and guess a little bit and guess and check. And chances are you will be correct. Of course, if we take a linear combination of those two, we can get any number in the third coordinate. But by this vector, if we have any linear combination of this middle vector, I know that the second position has to be twice the first position. So since this is the only vector affecting those two positions, that would mean in order for this to be a linear combination of these guys, we would need this guy to be half the fourth coordinate. So it's not. So this should not be in the span of these three vectors. And so we would go through the same process. Just find z perp. And that's just going to be z minus the projection onto V1 minus the projection on the V2 minus the projection on the U3. Now we don't need to subtract off the projection onto U3 in order to find a vector that's in W perp. But if we want an orthogonal basis for W perp, we're going to need this third guy or this fourth guy to be perpendicular to U3. So we might as well just subtract off that parallel component. So what are we going to get? 4, 3, 2, 1 minus our dot product. So let's go ahead and just compute everything. Our norm of V1 was 2. Dot product of V1 with this guy is going to be 6 in the direction of V1 minus norm of V2 was 5. And then the dot product of these two is going to be 3 and 4. So 7. And then lastly, our dot product between z and u3 is going to give us -4 and 2. So -2 divided by 2. So now going through the calculations, 4, 3, 2, 1, minus 3, 0, 3, 0. Fortunately, we did get some 7/5 in there. Minus 0, 7/5, 0, 14/5. And then now plus -2, 0, 2, 0. So what do we get?
Shouldn't the last column just be -1 and 1? Because the 2 canceled out.
Oh, yeah. I'm multiplying those 2's. Yeah. -1, 0, 1. So what do we get? 4 minus 3 minus 0 plus -1 gives us a 0 there. 3 minus 0 minus 7/5 plus 0 is going to give us 3 minus 7/5. So that's 15 minus 7, 8/5. Third row, we've got 2 minus 3 plus 1. So 2 minus 3 plus 1 gives us that 0. And then 1 minus 0 minus 14/5. So 1 is 5/5 minus 14/5. And then 0. So that'll give us what, -9/5. Did I miss any of the calculations somewhere? One is 5 minus 14 gives us 9. So this should be able to be chosen as our U4. Let's check it though. And let's write it as 1/5, 0, 8, 0, 9. I don't know if that's going to work. We might have done some computations wrong somewhere. Because we want this guy to be orthogonal to everything. So this guy, it's going to be orthogonal to V1. It's going to be orthogonal to U3. The question is V2. Sorry, that 9 was negative. I don't think it's actually orthogonal to, is it? Because if we take a dot product, we will get 8 minus 18, which gives us -10. So something weird is happening with this guy. Did we compute the dot product wrong with that component? So when we are subtracting off that component, it doesn't look like we did something right. We've got 4, 3, 2, 1. When I take a dot product, we will have 3 plus 2 is 6. Wait a minute. No, 3 plus 2 is 5. What am I doing? It's 3 times 2. Yeah, so we had 3 times 2. Dot product should give us 5. And then that's what I did. The numerator should be 5. So our dot product will give us 3 plus 2, gives us 5, and then the norm of this guy also 5. So that 7/5 was wrong here. This should have just been a 1. So that would make this guy a 1. And let's do it in red so we can see our corrections. So this guy should have been a 1. This guy should have been a 1. Or a 2, excuse me. And now, when we add them, so the first component we were good on, it was the second component. We will have 3 minus 1 gives us a 2 there. The third component we were good on, gave us a 0. And then this fourth component, we have a 1 minus 2, gives us that minus 1. And that's the vector we found. So this was the vector we guessed. But again, if you didn't know how to guess, or I mean, you shouldn't know how to guess or be able to see stuff like that, you should really follow through this process, especially because if the vectors aren't, if they're not nicely positioned with zeros in certain coordinates, you're going to have to go through this process anyway. And so this U4 vector gives us that distinct choice. Any questions on this?
Yeah, I sent something on the chat, but I guess you answered it. That we cannot use that little trick if the vectors are not set nicely in terms of like there's 0 in certain positions.
Right, exactly. That's what I was saying. That's how I came up with that red guy to begin with. That I know that the two vectors we were originally given have to be orthogonal because there's, zeros in the non-zero components for the other vector. And how did we find this U3? Well, we actually found this U3 by doing the process, but when we actually found it, we saw that we just switched the non-zero components, which were only 2. So if there's only 2 non-zero components, and then you take the negative reciprocal, right, for perpendicular lines, so you switch those components and put a negative sign, I know that that guy will be orthogonal to that guy. And of course, because the zeros are in corresponding positions, these two will have a 0 dot product. And nicely enough, because of those positions, we could guess this fourth vector. However, in general, it's not going to be that nice because we may not have zeros directly here, and it might not be that easy.
Okay.
So going through the projection process, make sure you know how to do. And again, typically, if you want to find a vector that is not in the span of 3 of them, pick a random vector. We probably could have even picked like something like 1, 0, 0. So check, you can always check something easy, like from these first 3, could we have gotten 1, 0, 0? Well, in order to get a 1 in the first position, I need sort of reciprocal multiples of this guy. So if I take 10 of these guys, I would need 9 of those to subtract off. But as soon as we do that, then this third position is going to be non-zero, which means I can only use one of those guys. But as soon as I pick one of those, you can kind of argue to yourself, come up with some loose justifications. You don't have to prove that this guy is not in the span. The thing to do is to kind of think through of, what are the odds that it is in the span? If you pick a random numbers and you can easily find a linear combination of the other 3 to get it, avoid that vector. In general, if you just kind of pick some random numbers, it's not going to be in the span. And then you can go through the process to find the fourth one. Now, this does bring up an interesting point. So everyone comfortable with this, finding orthogonal projections, creating orthogonal bases, finding orthogonal complements. Any questions on that? So there will be a question similar to this. You're going to be given essentially 2 equations that define a plane in 4 dimensions. you will have to use those two equations to find the span, or to find a generating set, find a basis for the subspace defined by those equations. Go through this kind of same problem, given a point not on the vector space. Find the distance, find the point in the vector space that's closest to it, and then maybe find a fourth vector to complete the complement.
I have a question about that fourth vector thing.
Yeah.
It seems like a much easier way of doing that rather than like trying to pick a random vector that's not in the span and then going through the like finding the perpendicular component of it. If instead you just picked, like once you had 3, if you just picked an arbitrary vector like A, B, C, D, and then you set the dot product of that and each of those other 3 vectors equal to 0, and then just row reduce that like a system of equations.
Yeah, that would work. I would be hesitant to do that, only because if everyone's paying attention to what was said there, that is another way to do it if you would like. For me, this is actually easier in some sense, right? Like you just said, we want to define these equations as the dot product of each of those vectors is equal to 0, right? Well, if you have that as a system of linear equations, we're kind of doing those calculations already in these projections. This is a straightforward algorithmic way to do that. You wouldn't be wrong is if we had our 3 vectors. So let's go ahead and write them out again. 1, 0, 1, 0, and 0, 1, 0, 2, and 1, 0, 1, 0 with one of the signs flipped. And now, so I'm sorry, that was Zach talking, right? Yeah.
Yeah, that was me.
Yeah, it was Zach. So what Zach was saying was, let's just start with some ABCD, and I want this to be orthogonal to all of the other ones. And you could come up with a system of linear equations by setting the dot product equal to 0. So that means A plus C is going to equal 0 from the first one. That means B plus 2D is going to equal 0 from the second one. And then minus A plus C is going to equal 0 in the third one. So it'll work, but again, if these numbers have non-zeros in them, it's going to be a little more complicated. And then, of course, since you know how to solve systems of linear equations, again, these techniques come up time and time again. And actually, this is another good point of linear algebra and sort of higher geometry in general. Since we have all these tools now, there's a lot of different ways to solve problems. So if you find a better way and want to try it, if it makes better sense a different way, perfectly fine. In this case, what we would do then is that have our 1, 0, 1, and then our 0, 1, 0, 2, sorry, 0 there, and then minus 1, 0, 1, 0. And then we want to look for our solution of 0, 0, 0. And so our problem with this is, well, you got to row reduce. This one probably won't be hard to row reduce since you've got a bunch of zeros there. So it should be pretty straightforward. It looks like you can probably get it with maybe one operation, in this case, adding the first row to the third one. Of course, since you have 4 variables, it's not gonna, you should have 1 degree of freedom. Of course, hopefully everyone understands that if I take this vector and multiply by a scalar multiple, still gonna give us an orthogonal basis. So we should have at least 1 degree of freedom. And then from that, you can use that degree of freedom to describe your A, B, C, and D. So for example, if we went through this, let's just add them since it's so quick. Add row 1 and row 3. And so that's going to be 0, 0, 2, 0, 0. And remember, that's our A, that's our B, that's our C, that's our D. And so what do we find? We find that C is equal to 0. We know that A plus C is equal to 0, so that A is equal to 0. And then that gives us our B and D equation. So B plus 2D equals 0. And those are our freedom. Pick one of them as your degree of freedom. So we can pick D equals 1, and then so our B would be -2 to find exactly what we found, up to a minus sign, I guess, on that one, which is still a good vector. So that would work. It's just, how many steps do you want to do it? I think row reduction with arbitrary vectors there, row reducing can get a little more tedious, a little more time consuming. It'll work, but here, I mean, it was more straightforward. Again, on the problem solving methods of row reducing, you have to choose your scalar multiples, choose what operations to do. This one is just straightforward computations. As long as you're keeping track of all your computations, it'll get it to you fairly quick. Sorry. So, Louis, you had an extra question. Luis, sorry. So, loosely, the Gram-Schmidt process allows us to find a new basis, orthogonal vector, to a given set of independent vectors. Yeah, essentially. Like if we were in R3 and we wanted to get a higher dimension, we could use this process to find a new basis vector. Yeah, exactly. That's very much what the Gram-Schmidt process can do in some sense. Like if we can always extend bases and extend them orthogonally. So we saw this semester of how to extend bases, or this idea that if I have a basis for a subspace. So in this previous example, we had a two-dimensional subspace that sits inside a four-dimensional space. And so not only can we expand the basis for that subspace, so if we started with two of them, we know that I can expand upon that basis to get R4. So I can always find two other vectors so that the span of those two vectors will span R4. And so this is the big result of this section is not only can we expand upon the basis we're already given, but if the basis we're already given is orthogonal, or we can make the basis given an orthogonal basis, not only can we expand that basis, but we can expand the basis orthogonally, meaning every vector we add in to include a higher dimensional set is going to be orthogonal to the previous ones. And this Gram-Schmidt process gives us exactly that. Yeah. Other questions? Okay, so maybe in 5 minutes, let's just talk a little bit about orthogonal matrices. So I don't know if this will be on the test or not. If it is, it'll be fairly easy, fairly straightforward. I kind of want to just go over what I had mentioned in our email. So definition. So a matrix, we're going to call it U. It's an n by n matrix, is orthogonal if, so the proper definition is that an orthogonal matrix, the transpose is the identity, or the transpose is the inverse. But another way of defining it, which kind of comes as a theorem, is that a matrix is orthogonal if and only if the column vectors form an orthonormal basis. of Rn. So in the previous example, we found 4 vectors that were orthogonal. If we wanted to create an orthonormal basis out of those, all we have to do is normalize them. So divide by each one by its individual length. And then if we took those bases elements, those vectors, and made them into a matrix, it would be an orthogonal matrix. So good examples are things like our rotation matrix. And R2. What is the transpose of this guy? It's going to be the same thing, just with a minus sign switched for that sign. And what happens when you compute the product? So do those computations real quick. Check to make sure that you get the identity. And we can show that they are inverses of each other. This was a special class of transformations that we called, these are Euclidean transformations of the plane. What are we doing with all the points under this R of theta? We're just rotating everything, right? So all of the angles between vectors and moreover the distance between points isn't going to change. If I just take the entire plane and rotate it, everything's going to look exactly the same, just in a different position. Distance the same, angles are going to be the same. And so this is a special case of what are called isometries. Let's call them distance preserving. Transformations. And not only are they distance preserving, but they're angle preserving as well. And how do we get that? Angle preserving is determined by a dot product. So if we're given u and v, the angle can be found in terms of the dot product up to scalar multiple. Right? And so the important thing about these orthogonal matrices is that we showed on the previous exam problem that if we have a dot product, so namely when we're taking a dot product between two vectors, this is really the same as the matrix product, where I just take one of them as a transpose, make one of the vectors a row vector, and then do a matrix product. And so if we have a linear transformation acting on one of the vectors, so this is going to transform this vector into a different vector, and then dot product with v. Well, this is the same as taking the transpose of this guy, dot product with v. And from our properties with transpose, right, we can think of our vectors as matrices, as n by 1 matrices. And so this is going to be the transpose of u times the transpose of a, since the transpose flips the order of the multiplication, and then dot product with v. And now you got to do a little bit of finagling, or actually not even dot product here since it's a matrix product. You can kind of think of it as UT times the matrix product of A transpose with V. And now since this is a matrix product, this is really U dot product with A of V, A transpose V. So in other words, this is where the transpose comes about. It is an adjoint operation, meaning that if I want to flip it on the other side of this inner product, applying a matrix to a vector inside of an inner product would be the same as applying the transpose of the matrix on the other vector in the inner product. And what is this going to mean about or what's this going to mean for orthogonal matrices? Well, if we apply this transformation, let's call them x and y, on two vectors, x and y, where let's take the dot product of these two vectors. So x and y, they have some dot product, and that dot product is going to determine the angle between them. And now if I hit both of those vectors with the transformation defined by u and take the inner product, well, by what we just showed, it's the same as if I move one of those u's onto the other side of the inner product. But by the special property of orthogonal matrices, this UTU is just the identity, meaning that we get the same inner product. So since orthogonal matrices preserve inner products, it didn't change the inner product of x and y. It's going to not only preserve the angles, but it will preserve the distances, right? What is the distance between x and y? Is just the length of the difference. But that is just going to be, I'm going to write the inner product as this angle bracket, which is a little more common for linear algebra. So this is a dot product between the quantity x minus y, the vector x minus y. And since if I hit both of those with the isometry with u, if we apply u to x minus y, again, it's not going to change the inner product, meaning the distance between two vectors isn't going to be affected by these orthogonal matrices. So these orthogonal matrices are very important to study, especially higher dimensional spaces when we want to preserve these distances, when we want isometric transformations. Take a look at that as if you're curious as well. Just to touch up on complex numbers. You want to think of complex numbers as matrices of this form. And you can kind of check that if you have a plus bi times c plus di, where I squared is going to give us -1, check that multiplying two numbers like this is the same as doing the matrix multiplications. Likewise, so just 1 point, this is our a plus bi. Then that means I corresponds to what matrix? To that matrix there. Where have you seen this matrix before? I claim we just wrote it down. What angle do we need? So I corresponds to a matrix, to a rotation matrix in terms of a rotation of pi over 2. So I don't know how much complex numbers you have seen yet. I hope you get to see them eventually. They're going to be highly useful in all sorts of higher level math and physics and engineering. But brief introduction to complex numbers. You can really think of complex numbers as a two-dimensional vector space as R2, where here we have our real axis, and then whenever I have b times I, think of it just as a scalar multiple of I. And so a plus bi is going to be a vector with b as this side and a as this side. And when we multiply by complex numbers now, it's just multiplying by this matrix essentially, meaning that when we multiply a number by I, corresponds to rotating that number in the plane by 90 degrees. So good stuff there. Take a look at it in the book. If you're curious about that stuff, feel free to email me as well. Even after the semester, if you ever have any questions on any of this stuff, let me know how you guys are doing. Let me know how you're doing in your future classes and all that. Any other questions? All right, so it's been great having you guys this semester. I will see you guys tomorrow, and then we will take the exam and get you guys' grades ready.